Okay, let's see an example. How do we actually prove a set is an orthogonal set? So here we have, actually in the set, we have two different types of elements. So let's call the first element f naught. So the first function is just one. And then all the other functions, I can actually name them in a more succinct way. So I can just call this cosine of nx. N is equal to 1, 2, 3, and etc. Right, so here, just the first one is not in the format of a cosine, but all of the other ones, you can just represent this as a cosine of nx. So our goal is to figure out, right, so if you pick any two indices, you can pick one of them to be 0, and the other one to be anything inside of this n, as long as it's not 0. So we can first prove that this equals to 0, right? So that is one step. So let's just plug everything we have here in this question to prove that if you just do f naught, which is 1, times any n, right, cosine of x n dx. So in this case, we're going to integrate this. So when you integrate it, remember the formula of cosine, so it becomes sine of nx. So here we are going to do a bar with negative pi to pi. Okay, so now we can plug pi inside of x. So 1 over n sine of n times pi minus 1 over n sine of n times negative pi. Okay, so with sine, any multiple of pi gives you a 0. So of course, when you have sine of n pi, whatever n integer n that would be, this will give you a 0. So check. We have proved that this, if you picked one of the index to be 0 and the other index to be anything integer, 1 and above, then we have it, right? We have the inner product. Sorry, there should be a dx here. So we should have an inner product equals to 0. X equals to 0. Okay, so now let's do, are we done now? If we just prove that if you can pick one of the index to be 0, the other index to be any constant that's larger than 0, are we done with proving the whole set to be orthogonal? No, because we said that to say a set is an orthogonal set is for any two indices, so any pair of index you find. So it's not necessarily one of the index has to be 0. So we have another step to prove, which is if you randomly pick two index, one is m, one is n, all from this, right? All from like when n is greater than or equal to 1. So we have to prove that this also holds, right? This inner product also holds. Okay, so let's do our calculations here. So you can have cosine of mx times cosine of nx dx. Okay, so here we have to use the trig function to help us, the trig identity to help us to kind of make this integrand inside of the integral to be easier to integrate. So if you still remember, this is cosine of m plus n times x and plus cosine of m minus n times x dx. Okay, and then I should have another parenthesis here. So if you are not really familiar with how you got from this, how I got from this step to this step, I would encourage you to go back and check what is the sum, the double angle formula for cosine. So this is just a trig identity. For the sake of time, since this is not the key point of this class, I'm just going to assume that you can find a source and to convince yourself this is true. And then we can integrate this. So it's the same thing. You have 1 over m plus n of sine of m plus n x plus 1 over m minus n. So you have m minus n x sine of this. And then all evaluated from negative pi to pi. Okay, so here, because both m and n are integers, so, and also they are above 1, greater than or equal to 1 in this case, right? So for this one, we know that it's going to be a positive integer. So when you plug in pi to for the place of x, you see that this is still a multiple of pi. So sine of that would give you a 0, right? So are you convinced that? So for the first item, when I plug in x equals to pi, so this is sine of some positive constant times pi, which this is 0, right? And then for the other one, since m and n are not equal to each other, so when we pick the m and n, we want them to be different, right? So first of all, this fraction cannot be 1 over 0 because m is not equal to n. And what we have here, so without loss of generality, we're going to assume that m is greater than n. So still, this is going to be equals to 0 as well because it's a constant multiplied by pi. So this is also 0. So in the end, we have the whole inner product equals to 0 for this case as well. So this is also checked. Okay. So in this case, we prove that no matter what case you fall into, either you choose 0 as one of the index and the other index come from here, or you picked 2 of the indices, both from when n is greater than or equals to 1. So in both cases, the 2 functions that you picked from the set are orthogonal. So we say that this whole set is an orthogonal set.